Today we're going to talk about continuity, and this is going to be one of our first uses for limits. Continuity is also going to be important because it's going to underlie a lot of the theorems that we'll learn later in the semester. And you've maybe in a pre-calculus or algebra class thought about what it meant for a function to be continuous. So think about what was that definition of continuity? How did you describe continuity in a pre-calc class? And it might have been something like you can draw a graph without picking up your pencil, and that's a continuous graph. And that's a decent definition of continuity. We're going to make that definition a little more precise. So let's draw a few examples of things that are not continuous. So things where we actually have to pick up our pencil in order to draw the graph. So we could draw something maybe with like an asymptote. In order to draw both pieces there, I have to pick up my pencil and draw the other half. So this is discontinuous at whatever x value this is here. We could have something that has a jump in it. So maybe something like this. Whoops. Something like this would be discontinuous at this point A. And we could draw something, maybe something that has a hole in it is discontinuous because think you have to pick up your pencil to get on the other side of that hole there. So this would be discontinuous at this point, okay? So if we look at each of these discontinuities here and think about them in terms of limits, the thing that we notice is that the value of the function is not equal to the value of the limit. So in this case, we have the limit as x approaches a of the function is infinite, but f of a is undefined. So there's not a value for the function at that point because of that infinite discontinuity there, or that vertical asymptote. That's really how I should phrase it right now. This one here, that limit as x approaches a does not exist. Here, this limit exists. Maybe this value is 1 and this value is 2. So the limit is 1, but the value of the function is 2 at a. So the limit and the function disagree. So if the value of the limit agrees with the value of the function, then our function's continuous because it's kind of a nice little line. But if the value of the function and the value of the limit are not the same, then our function's discontinuous. So we say a function's continuous if the limit as x approaches a of f of x equals f of a. So if we picked like this value here to be our a, the limit is that point, that y value, and that's also the value of the function there. Okay. So you can still think about the same way of defining continuity. If I can pick up my pencil, if I have to pick up my pencil in order to draw the graph, then my function's discontinuous, but also think of it in terms of limits. So if we look at this graph below, I want to know where this graph is discontinuous and why. So go ahead and see if you can think about where is this going to be discontinuous. So spend a second thinking about this before you keep watching me do this. So I would say that this function's discontinuous at 2, at 4, at 5, and at 8. And so let's write that as x equals 2, x equals, no, not at 3, x equals 4, x equals 5, and x equals 8. And let's think about why that's the case in each of these. So the limit as x approaches 2 of our function does not exist. Since that limit does not exist, it cannot be equal to the value of the function. Okay, the same is true at x equals 5. That limit does not exist. And so once again, since the limit does not exist, that's not equal to the value of our function. And so saying a limit does not exist is a good enough reason to say that a function is discontinuous. And then at x equals 4, the limit as x approaches 4 is 3. But that's not equal to f of 4 because f of 4 was 1. Okay, so the limit exists, but the limit and the function do not agree at that point. So that's the problem. And at 8, the limit as x approaches 8 of our function is infinity, and f of 8 is undefined. If our function is undefined at a point, then it can't be equal to the value of the limit. Okay. If each of these discontinuities behaves a little bit differently, notice one's got a vertical asymptote. At these two, we have like jumps. That was at 5. And then this one kind of just that point was moved. And we'll talk about each of these different types of discontinuities in class. We'll give them names like jump, removable, and infinite discontinuities. But just saying a function's discontinuous is kind of not enough. We notice that like this point kind of behaves nicely, and so does this point, but this one doesn't. These have open circles. So we can talk about continuity from the left and from the right. And really all we do is we take this limit up here and we replace it with a left or a right-hand limit. So let me write that down and then we'll talk about it. So we say a function's continuous from the right if the limit as x approaches a from the right is equal to f of a. And the limit is, or it's continuous from the left if the left-hand limit is equal to the value of the function at the point. And we say a function is continuous on an interval if it's continuous at every number in that interval. Okay, so if we look at this graph above, we look at this like at x equals 2, we can say that f is continuous from the right at x equals 2, since f of 2 is 1, that's where the closed dot is, and that right-hand limit as x approaches 2 is also 1. These are equal to each other. Okay, we kind of noticed that's because the closed dot is on like the right-hand side of the line. At 4, this function is neither continuous from the left nor the right because the closed dot doesn't meet up with either side of the line there. At 5, this function is going to be continuous from the left because the closed dot is on the left-hand side of 5. And so we have a limit as x approaches 5 from the left is 4. And that's also f of 5 is equal to 4 because that's our closed dot. And so f is continuous from the left at x equals 5. And then the function is neither continuous from the right or the left at 8, since f of 8 is not defined. Okay, continuity is really going to be an important basis for a lot of the theorems we talk about later in the semester. So that's why we're talking about continuity now.